So the title of this talk is UWare, Software-Defined Ultrasonic Networking for Wearable Devices. This is a joint work between me and my advisor, Tommaso Melodia, from Northeastern University in Boston. So, wearable devices are the cornerstone for many revolutionary medical applications. In fact, there already exist several devices that can be used for medical purpose. For example, we have wireless EEG that can be EEG that can be used for brain performance tracker or mental fitness tracker. Again, we can also talk about wireless EKG, so electrocardiogram, for having remote cardiac monitoring for early diagnosis of arrhythmia or hypertension in order to prevent heart failure or strokes. Another interesting device is wearable skin patch. For example, these are very useful for creating closed feedback loop drug delivery systems. So, for example, the artificial pancreas, where we have one sensor measuring the level of glucose in the interstitial fluid, and then sending this information to another sensor where we have an insulin pump, and we inject a specific amount of insulin based on the reading of the sensor. Of course, here we need a communication between wearable devices. And also, of course, everybody knows a wireless motion tracker, which today is basically used for fitness purposes. However, it can enable a lot of medical applications, for example, post-surgery telerehabilitation, or, for example, to monitor the motor degradation in Parkinsonian patients. So the question is, with the number of the wireless increasing in the future, how are we going to connect these devices? Today, these devices communicate using radio frequency electromagnetic waves. Specifically, they use technologies such as Bluetooth or Wi-Fi. Now, these technologies, however, comes with some limitations. For example, first of all, the RF spectrum is already crowded with many interfering devices. So coexistence with existing RF system is a big problem. Moreover, RF communications can be easily jammed and eavesdropped. For example, any smart kid with a very inexpensive radio can jam on RF communication. Potential safety risk. The medical community is still divided on potential risk coming from the absorption of RF waves by human tissues. And finally, RF propagation issues. An antenna, when it gets in touch with the body or in proximity to the body, is affected by the dielectric nature of the body itself. That means, for example, the central frequency will shift, the gain will decrease, and so the system design will change. So for all these reasons, we propose UWare, which is an alternative to RF. Basically, it's a software-defined framework for networking wearable devices based on ultrasonic communications. Ultrasonic waves, are acoustic waves whose frequency is higher than the upper threshold of the human hearing. So basically, it's just sound that we cannot hear. So it has been used for a while in underwater communication, also in indoor localization, as well as gesture recognition, and of course in medical imaging. In the last few years, we've been proving the feasibility of ultrasonic communications for implantable devices. UWare comes with a couple of advantages over RF. First of all, we don't have conflicts with RF systems. We are using a different physics, so there is no RF. Secondly, it's hard to jam and eavesdrop. Ultrasonic waves do not go very far in air, and moreover, they do not penetrate solid materials. So jamming and eavesdropping requires some sort of closeness between the attacker and the victim. We don't have safety concern. It has been used for the last 70 years for medical imaging and proved to be fundamentally safe. Moreover, if we have an ultrasonic intra-body network, we can use these wearable devices as a bridge between the intra-body network and the external world, so the internet. With the same transducer that we use for transmitting and receiving, we can also do acoustic localization, which is known to be more accurate than RF localization. And finally, we can achieve real-time reconfigurability since our framework is software-defined. So we can adjust the networking scheme based on the application layer requirements. Now I'm going to first cover a little bit the basics of how to generate ultrasonic waves in air. Then I will talk about the architecture of UWare, present the two prototypes that we built, and then talk about performance evaluations. About the basics, how do we generate ultrasonic waves? This is done through ultrasonic transducers, which are devices that convert electrical signals into pressure signals, which means ultrasounds, and vice versa, of course. Are coupled because we need to communicate through air, so we talk about ultrasonic airborne communications. And today, thanks to MEMS technology, we are able to build micro machine ultrasonic transducers, which are very small transducers that can still receive and transmit efficiently ultrasonic waves. Finally, If we work in this specific range of frequency, which is between 17 and 22 kilohertz, we call near ultrasonic range, we can generate and receive ultrasonic waves using commercial off-the-shelf smart microphone and speakers. That means a UWare can perfectly run on a general purpose device, such as a smartphone or a tablet or a smart TV. So, UWare is a collection of software-defined multi-layered functionalities that we use for networking wearable devices. It runs on a general-purpose hardware, so it could be a microcontroller, microprocessor, or even an FPGA. And this is interfaced through the hardware through hardware-specific system APIs. And basically, we generate the waveforms in the UWare. These are then converted in analog, DAC, and then goes to the communication unit and transmitted. Vice versa, we receive the signal, we go back to digital, and then UWare processes the data. UWare comes in multi-layer solutions with physical, data link, network, and application layers. At the physical layer, we have two fully functional modulation, GMSK and OFDM. Then we have also synchronization, channel estimation, forward error correction coding, and equalization functionalities. GMSK is a continuous phase modulation and has a very high spectral efficiency, and it's perfectly for those narrowband near ultrasonic communications. While OFDM, on the other hand, is very robust to frequency-selective channels, and that's why it's perfectly suitable for ultrasonic wideband communications. At the data link layer, we have medium access control protocols, deterministic such as polling or random as ALOA or with carrier sensing as CSM-ACA. And the UWare supports two different network configurations. We have a master slaves, where we have a network coordinator with higher resource, such as a smartphone, for example. And this is perfect if you want to continuous monitoring data coming from the body. Or we also have a peer-to-peer configuration in which we have all nodes treated as peer, and for example, the closed feedback loop application when we need nodes to talk to each other. At the network layer, we have IPv4, IPv6 support, which is great if in the future we're going to talk about Internet of Wearable Things. And then we also have data-centric addressing, which is an easy way to fetch data from a small network. At the application layer, of course, we manage the user interaction. But especially we also have this reconfigurable and modular data processing. So basically the data coming from the sensors are processed by applications that can be decomposed in primitive blocks. Filters, data operation, detectors. So what we do basically, we are able to arrange these blocks to create easily new applications. And more importantly, we're able to install on the fly this application on the wearable device from the phone with no need of upgrading the firmware because everything is done at the application layer. So let's move to the implementation. We have two prototypes, the view mode and the view master. One is the sensor, the other one is the smartphone, the network coordinator. This is a general architecture of view mode. We have a core unit with memory and processing unit where UWare is running. We have a communication unit, power amplifier, the transmitter, low noise amplifier, the receiver, and a couple ultrasonic transducers, of course. Sensing unit can be everything, an accelerometer, a gyroscope, a glucose meter, or even actuators, for example, a neurostimulator. Power unit, we need a battery, of course, and also we can have a wireless energy transfer unit for transferring energy to wirelessly charge the battery. This is a picture of our implementation on a breadboard, and here we have that the core unit, so processing and memory, is implemented using the TNC 3.1 platform, which is a very tiny development board that embeds an ARM Cortex-M4. We have a power amplifier. Then we have a microphone, MEMS microphone, and in the board we also have a low noise amplifier. And finally we have the speaker, that is the one that is actually producing the ultrasonic waves. The software, as I said, is running in the processing unit. In this case, is running on the Cortex-M4. This is the software architecture of our system. We have the system APIs, which are the analog input and output. Then we have a GMSK transceiver. In a way, it's not correctly showing the text, but okay, it's a GMS transceiver that also implements forward error correction, synchronization, or also equalization and the channel estimation. At the data link layer, we have an adaptive polling and ALOA. We implemented a binary mask-based data-centric address in this prototype, and also we have a set of primitive blocks, for example, filters, functions such as find peaks or get distances. That's why, because we want to have the reconfigurable application layer, we focus on two different classes of applications. One is, for example, an ECG trace. The other one is coming from a 3D accelerometer. So, for example, if we consider the ECG trace, we have, if we filter out the frequency we don't need, we detect the peaks, which are the ventricular contraction, for example, and then we count the peaks over 60 seconds, or over 6 seconds and multiplying by 10, we obtain the number of beats per minute, which is exactly the heart rate. Or another application, for example, for the accelerometer, we consider a three-dimensional vector. Then we have the toe-off moment when the foot is leaving the ground, while the other one is heel strike when the foot is hitting the ground. So basically, we get the magnitude of this vector, we filter out, we do a peak detection, and we basically count the steps. So basically, by arranging these simple blocks, we're able to process different kind of data and get useful information for the user. The ViewMaster is basically prototyped on top of an iOS platform, so it runs on Apple iPhone phones. We use the VDSP library provided by Apple, which is very useful for complex operations such as FFT or convolution, so that was great for implementing the physical layer. Then we have NovoPane, which we use it for accessing the hardware, the audio hardware of the device, and WIT framework, which is basically a speech recognition system. The software architecture is very similar to what we had seen before in the view mode. We have again our NovoPane in this case is doing the system APA work, basically input and output. Then we have a GMSK transceiver which was built mostly using the VDSP functions. And then we have WIT at the application layer that let the user give commands just using the voice and fetching data from the network. The GUI, we implemented different views. For example, we have a physical layer for sending and receiving packets in order to test in terms of bit array, or fetching the data in the network just using, for example, the voice, or installing on-the-fly application leveraging the reconfigurable system that we developed. Performance evaluations, we test our system in terms of physical layer, MAC layer, and application layer. At the physical layer, we have test our system in terms of bit array. We consider two different scenarios, line of sight, 50 centimeters apart between the ViewMaster and the view mode. And then we have near line of sight, we have a handheld device, and then we have a node on the chest, another one is on the leg. These are snapshots of three different channel impulse response. Line of sight, we have just a single path, of course. Then we have chest-hand scenario, we have a second path, probably a reflection between the hand and the chest of the user. And then we have leg-hand scenario in which we have multiple reflections, probably due to multiple reflections between the trunk and the hands of the user. We test our system in terms of bit rate as a function of the SNR. In line of sight, we observe that, of course, by increasing the SNR, we are decreasing the bit rate. And we also plot different curves for different forward error correction coding rate. So we have uncoded communication and then 8/9, forward 5, 2/3, and 1/2. By decreasing the coding rate, we are basically increasing the robustness of the system. So we have lower bit error rate. But at the same time, we are reducing the data rate. We go from 2.76 for the encoded kilobits per second down to 138 kilobits per second for the 1/2 coded. So we trade reliability for data rate. For near line of sight, we have very similar results. The trend of the curve is pretty much the same. We need 1 dB more in the chest-hand scenario to obtain the same SNR, the same bit rate as the line of sight. And then we need 4 dB more of SNR in the leg-hand scenario for obtaining the same bit rate of the line of sight. In terms of MAC layer evaluation, we test it in terms of data delivery delay, so how much time we need to fetch the data. We consider a scenario with 4 nodes 40 centimeters apart from the ViewMaster. And I'm showing here the adaptive polling case. Adaptive in the sense that every time there is a retransmission, means a packet is lost, we are able to lower the coding rate so we can increase the robustness of the system. This is possible just because we're using a software-defined solution where we can perfectly adjust the physical layer functions from the upper layer, for example, in this case, from the MAC layer. In terms of increasing nodes, since the polling solution is a deterministic protocol, we have a linear increase. But if we test the delay as a function of the SNR, we observe that higher coding rate means low robustness, so we have higher retransmissions, and that means higher delay for low SNR. When the SNR increase, a code for 5, which means more robust, it's too much, so we have underutilization of the system. So thankfully, we can use our adaptive solution. So what we have is that the FEC can be adjusted to the SNR level. So basically, we are able to reduce the retransmission for low SNR and reduce the underutilization for high SNR. Finally, application layer, we test our system in terms of processing accuracy. So we try to understand how good our view mode is able to do the measurements. For example, here I'm showing the accelerometer processing. We recorded 3D traces, 3D accelerometer traces, using an application for iOS called SensorLog. We test different scenarios, walking, running, climbing up and down the stairs, and we test the view mode estimation of those traces, so how many steps the view mode is counting, with the number of steps that are counted by the iOS platform, and finally the real steps, the one that are actually counted by the user who is performing the steps. And we obtain an accuracy of 94%. So we're basically showing that our reconfigurable system, other than being flexible, is also pretty accurate. And with this, I'll conclude my presentation. I will be very glad to take any question.